everyone. This is Professor DePaulo. Welcoming you back to Psych 220, fully online behavioral statistics. And this week we're going to be talking about the t-test for related samples. Sometimes it's known as repeated measures t-test. It's also known as paired samples t-test. It's also known as within groups design. So there's a variety of ways to describe it. But in this situation, you have two related samples, and generally, most of the time, they're the same people in each condition. So you have two conditions, like before and after, and you have the same individuals before and the same individuals after, and you want to see if there's a difference between those two. That's what happens in the majority of cases. So some of the learning outcomes for this week's chapter include the structure of a research study that is appropriate for repeated measures t-test. So when do I use the repeated measures t-test versus when do I use independent groups t-test, and how do I report it in the research? To actually compute the mean difference between those two conditions, usually before and after, in the repeated measures t-test. To evaluate the effect size using Cohen's d, r squared, and or confidence intervals, which we've done before, and explaining the benefits and the shortcomings of using repeated measures and independent measure studies. So what's the benefit of using repeated measure design versus what are some of the drawbacks? And what's the benefits of using independent groups design, and what are some of the drawbacks? So with the repeated measure design, as I said before, also known as within subject design, paired samples design, those are synonyms for the same thing, right? Two separate scores are obtained. So if it's strictly repeated measures, you have the same individuals in the two conditions, and you have two scores, and you want to compare those two scores for those same individuals. There's no risk of the participants in each treatment group differing significantly from each other. So with an independent group design, there's a possibility that the two samples are different with regard to a lot of things, right? And one sample or one condition might have an advantage at a particular task because of the makeup of that sample. Well, in the case of repeated measure design, you don't have to worry about that because you have the same individuals in two conditions. So you don't have to worry about, well, the group that got the experimental treatment might be fundamentally different than the group that got the control treatment because maybe they were younger or more intelligent or something else was wrong with them, right? You don't have the case here because these are the same individuals. So you don't have to worry about the difference between the two samples. And that's one of the advantages. Now, saying that, if you use random assignment with a large enough sample, you shouldn't have to worry about the independent groups design either. Because if you're randomly assigning with a big enough sample, the independent groups, the independent samples should be relatively balanced out with regard to all these extraneous variables, these confounding variables that, there's not going to be an advantage for one group or the other with a large enough sample. With a small sample, there's that possibility of one group being biased versus another. But with a large enough sample and random assignment, that usually takes care of the independent group design. And the reason I say that is that it's not like let's all run to do repeated measures design because we don't have to worry about the sampling variability. That's usually not that big of a concern if you're doing random assignment, which you should be doing with the independent groups design. So how do we compute this? It's the same as the one sample t-test. The only difference is that we're using different scores rather than raw scores. So it's basically a one sample t-test based off of the different scores. And the different scores are the second group score minus the first group score. So each individual has two scores. You subtract one from the other, and that gives you the different score. That's all it is. It's the difference between one group score versus the other condition score. And if you make those different scores and then you run the t-test like you're doing a single sample t, you'll get the same answer. It's the same deal as that. So it's just like doing a single sample t-test, but you're doing it on the difference scores. So make the difference scores first, then do the t-test. The mean difference is the sum of the difference scores divided by the total number of people in the study, n, the sample size. So all you do is add up the difference scores, divide by n, that gives you the mean difference. And then to find the standard deviation, all you do is you compute the standard deviation or the standard error with the sample, based on the same formulas you use to find standard error with a single sample t. Now the hypotheses for the repeated measure design is the null hypothesis says that the mean difference is 0. So there's no difference between before and after, which is generally what you're looking at with repeated measures, before and after. There's no difference. The alternative, if you're doing non-directional, the two-tailed says that there is a difference. So that mean difference is not 0. If you're doing one tail, you need to specify, is the difference going to be greater than 0, or is the difference going to be less than 0? That would be a one-tail test, a directional hypothesis. But if you're doing non-directional, you just say that the mean difference is not 0. It could be positive or negative, but it's not 0. So it's basic as that. So here's an example of each subject. They have a score in condition 1, and they have a score in condition 2, and then they have a different score. So if you look at subject A, they have 10 and 14. And if we're doing condition 2 minus condition 1, which we're doing in this situation, we're doing 2 minus 1 to find the different scores. 14 minus 10 is 4. 13 minus 15 is negative 2. 15 minus 12 is 3. 12 minus 11 is 1. If you're doing a non-directional hypothesis, two-tailed test, it doesn't matter which direction you subtract. So if you subtract 2 minus 1, that's what I did here. But if you did 1 minus 2, you get the same answer, but the signs would be switched, which won't make a difference with a two-tailed test. The only time it makes a difference which group you're subtracting is if you have a directional hypothesis. Like, for instance, let's say that I think that group 2 is after, or group 1 is before, and an after is going to be better than before. Let's say I did some kind of intervention, and I said afterwards, you're going to score higher than before. Well, in that case, I want to do after minus before to look for a positive number. So if I do group 2 minus group 1, I expect a positive difference score, because if I'm hypothesizing that after is better than before, I'm expecting a positive value there, right? If I'm hypothesizing that after is less than before, then I would expect a negative value for the difference scores. And so when you have a directional test, you need to interpret the sign of the different scores in terms of what your hypothesis is. Are you expecting an increase or are you expecting a decrease? But with a two-tailed test, it doesn't matter, whether it's negative or positive, because you're looking at both tails. It doesn't matter which group you subtract from which other group. And once you got the different scores, you compute the mean of those different scores by adding up those different scores and dividing by n. And that gives you the numerator, the mean of the different scores. You see mean of different scores minus mu of different scores. Mu of different scores is going to be 0. So the null hypothesis pretty much always is going to say that there's no difference between the groups. There's no difference before versus after. So you would make that to be 0. So that mean different scores minus mu different scores, the numerator of this t statistic here, is you're just gonna cross out mu different scores. You're gonna make that 0. So really it's gonna be the mean of the different scores in the numerator by itself, because you don't have to write minus 0. Minus 0, just erase that, right? Just put the mean of the different scores in the numerator, and then put the standard error of the different scores in the denominator. So how do you find the standard error? You compute the variance. So if you have the sum of squares, and you have the degrees of freedom, which is n minus 1, or number of different scores minus 1, you can compute the variance. So you get the sum of squares, you divide it by n minus 1 or different scores minus 1, and you get s squared, the variance. Then if you take the square root of s squared divided by n, you'll get the standard error. So that, if you simplify that, it becomes s over the square root of n, and that gives you the standard error of the different scores. So once you have the mean of the different scores and the standard error of the different scores, you can have your t-value, you're done. Just like you did the signal sample test, except instead of raw scores, you're using different scores. That's the only difference. Let's look at when it's appropriate to use a repeated measure design. So A, a group of twins is tested for IQ. Well, those are two different people. They're related. You can even say that could be considered paired samples tests, which we'll talk about briefly afterwards. But it's definitely not repeated measures, because repeated measures means you need to have the same person in both conditions. So A is not good. Comparing boys and girls' strength at age 3. Boys and girls are different, so that's not good. Evaluating the difference in self-esteem between athletes and non-athletes. Once again, athletes and non-athletes are two different groups, so that doesn't work either. Students' knowledge is tested in September and December. Well, here we have one group of students, and we're testing them twice. So that would qualify as repeated measures, the same people being tested multiple times. And that's the answer. The answer is D. Students' knowledge is tested in September and December. Same individuals tested twice would be a repeated measures t-test. Now, you could have the same individuals tested 3 or 4 times. That would be repeated measures as well, but it would be beyond t. So t only is 2 conditions. Once I have more than 2 conditions, I have something called analysis of variance, which we're going to be doing very shortly as next week. And you're going to be seeing that you could have more than 2 conditions. So 2 conditions is always t. More than 2 conditions becomes ANOVA, analysis of variance. And there's a way to run it. It would be considered a repeated measures analysis of variance if I had more than 2 testing periods. But here we're just testing September and December, so there's only 2 groups, same individuals in each condition, and therefore it's repeated measures t-test. Let's look at these questions now. A repeated measures study requires 20 participants to obtain 20 scores in each of the conditions being compared. Well, the same people are in both conditions, so if I have 20 participants, I should have 20 scores in the 2 conditions, right? That makes sense. As the variance of the different scores increases, the magnitude of the t-statistic decreases. Well, that's what happens. Once the variance goes up, variance is in the denominator of the t-statistic. So as variance goes up, the denominator gets bigger, and if the denominator gets bigger, then the t-statistic overall gets smaller. So if the mean difference in the numerator stays the same and the variance gets bigger, the denominator is getting bigger, the numerator is staying the same, and therefore t is getting smaller. So these are both true statements. If each subject is tested in all treatment conditions, and there are 20 subjects, then you only need 20 subjects, right? And if there's 2 conditions and you have 20 subjects, they're tested in both conditions. That makes sense. If you increase the variance, obviously, of the denominator, that decreases the t-statistic. So you have to look at that denominator. It's the standard error of the different scores. So it's the standard deviation of the different scores divided by the square root of the sample size. And so as variance goes up, the standard deviation of the different scores goes up, and therefore the denominator gets bigger, the t gets smaller. So the numerator of the repeated measures t-test looks at the actual difference between the data and the null hypothesis value. So the null hypothesis value is always 0. So you simplify the numerator of the t-statistic, it's only the difference. It's the mean of the different scores. That's all it is. Because the other part, the comparison where the null is true is always going to be 0. So that numerator simplifies to just the mean of the different scores. You don't have to write mean of the different scores minus 0. Just write the mean of the different scores on top, and then on the denominator, you're going to have the standard error of the different scores. And the standard error is basically under the situation in which the null is true. So how much variability is there in terms of the sampling distribution when the null is true? This is the same thing as the one sample t. If you have a directional hypothesis, you need to state it. So maybe you think the different scores will, decrease. So basically, um, after is going to get, is going to decrease compared to before. Then you expect it to go in a negative direction, right? The different score should be negative if the after category is decreasing compared to the before category. Because if I do after minus before and after is smaller than before, I'm going to get a negative number. So if you have a directional hypothesis, you need to state the directional hypothesis. So it could be less than, it could be greater than, and that will increase the power. So a one-tailed test, a directional test, makes it easier to reject the null hypothesis. The problem with the one-tailed test is sometimes you end up with a mistake where you end up finding a result that's opposite of what you originally thought. And if you find a result that's opposite of what you originally thought and you're doing a one-tailed test, you cannot then reject the null hypothesis because you're not looking in the other tail of the distribution. As a result, a one-tailed test is frowned upon in pretty much a lot of research. I mean, people are going to question you if you try to publish something with one-tail tests. They're going to be very suspicious. They're going to say, "Why are you doing this? Why don't you use a two-tailed test?" Because they think you're going to use a one-tailed test just because it gives you an advantage. It makes it easier to reject the null, which it does. It gives you an advantage. But it's almost like the editors of these journals think that you're trying to cheat them. And so whenever I conduct research, I always analyze the data using non-directional or two-tailed tests because one-tailed tests are frowned upon with a lot of editors of journals. And I think it goes back to a lot of things. I mean, there's been some recently there was the situation with the Darrell Bem finding that I may have talked about already, where he showed that there were psychic powers. And this was not going back that long. This was going back to maybe 2010, 2011, where he published a paper, a pretty prominent paper in the Journal of Personality and Social Psychology, where he showed that people were able to guess at better than chance what someone else was thinking about in a different room. And he said this is proof of psychic powers, right? And there's been a long interest in psychology. You had a field called parapsychology that dealt with paranormal processes and people doing paranormal research. And that field has kind of fallen apart. There was a lot of pushback against parapsychology. And Darrell Bem was one of the parapsychology researchers, and he was at Yale. And he came up with this paper showing this, and the scientific community destroyed him. They just basically said this guy's a fraud, even though he was well respected. He was at Yale. He was in his 70s or 80s, I think, by the time he published this. So he was there quite a long time, so most of his career. And he got so much pushback from the scientific community. They just basically said his data is flawed. He ran one-tail tests. And so I think there's a little bit more of a pushback against people doing the one-tail test because of these situations that have happened with Darrell Bem and others, where they've tried to push more controversial topics and show that they work through one-tail tests, but not two-tail tests. So I think that's kind of gives you a little bit more of a feel of why two-tail tests are probably the safer bet, and you don't have to explain yourself to people. So that's kind of how I run the two-tail tests and try to stay away from the one-tail test. So that's a little caveat. Sorry about that. We also need to keep in mind the assumptions. The homogeneity of variance assumption only applies to the independent groups test, t-test. It does not apply to the repeated measures t-test or paired samples t-test. So we don't have to worry about that. We have to worry that the treatment conditions are independent. So before and after, they should both be independent of each other. Uh, and basically they are because they're done at two different times. So you wouldn't want to like have before and after scores that were identical, that were taken at the same time, but you're not going to do that. So this is kind of a pretty obvious thing to keep, keep separated. You should also have normal distributed difference scores, and the difference scores are generally normally distributed if you have a sample size greater than 30, and that's due to the central limit theorem. So if you have more than 30 in your sample, you're fine. If you have less than 30 in your repeated measure design, then you have to check to see if the difference scores are normally distributed. This is not a serious concern. If you had less than 10, this becomes a more serious concern. So the bottom line is get big enough samples, try to get them bigger than 30. If they're really small, it can be a problem. You have to check it. And if it's really small, you're going to have other problems. You're going to have an underpowered study. You're not going to be able to reject the null. It's going to be very difficult. So there's no use having a study with like 10 or 20 people. You should at minimum have 30 people in your study, at very minimum. To find effect size measures, you can use Cohen's d again. This is the mean of the different scores divided by the standard deviation of the different scores. Or you can compute r squared, which is the proportion of variance accounted for. And that's equal to t squared over t squared plus the degrees of freedom. In this case, the degrees of freedom are n minus 1. The number of different scores minus 1 is your degrees of freedom here. And also you can calculate the confidence interval. So if you want a 95% confidence interval, then you need to have the mean of the different scores plus or minus the two-tailed 0.05 critical value for t. So if I'm doing 95% confidence interval, I want a 0.05 two-tailed critical value of t times the standard error of the different scores, S sub m sub d. And you've calculated that for the t test. So, and then you just add and subtract that product from the mean of the different scores. Similar to what you did before with the confidence interval for the single sample. If you're writing this up to publish it, you want to report the t values with the degrees of freedom. You want to report the significance level, and you should report the effect size, although not everyone does. It's kind of useful to report the effect size. So for example, if you had 10 subjects, you'd report t parentheses 9 because you have 9 degrees of freedom with 10 subjects here. So t parentheses 9 equals 2.43. The p-value is less than 0.05. That means it's statistically significant. That means there's a difference before and after. And the r squared is 0.697, which is a pretty large effect. So that's a pretty strong effect here. There's a pretty strong difference between before and after. What factors influence the outcome of the hypothesis test? The size of the sample. So the larger the difference before and after means that there's a larger numerator, and that increases t. Also, the larger the sample size leads to a smaller standard error, which leads to a smaller denominator, which then indirectly leads to an increase in t. So if I increase the difference between the two conditions, I increase t. If I increase the sample size, I increase t. And if I increase the sample variance, I decrease t, because now my denominator is bigger, and therefore the t is smaller. So ideally, you would have a big sample, a large effect, which is the numerator of the t statistic, and you'd want to have a smaller variance, which would make the denominator smaller. Now, it's hard to control the variance, so the easiest way by far is just increase sample size. If you increase sample size, you're going to increase t. because the denominator is going to get smaller and t is going to get larger. So just keep increasing the sample size and you're going to get a significant result. That's kind of the reason why people have you report the effect size, because if you have a huge sample, pretty much any difference is going to be significant. But it may not be important. That's why they're requiring or they're asking people to report effect sizes now, so they don't just artificially inflate the t-value by increasing the sample size. So if I have 10,000 people in my sample, yeah, I'm going to have a big t-value, but does it mean much? It's going to be, is it big because you'll have such a large sample, or is it big because there really is a big difference? And that's where the effect size comes in, because the effect size does not look at the sample size. It only really looks at the difference between the conditions. And so it gives you a better measure, eliminating sample size from the equation in terms of how strong the effect is. The advantage of the repeated measures design is it requires fewer subjects. That sounds like not a big advantage, but it is, because if you're paying people, it requires less payment. And money is always an issue in research. You never have even if you have thousands and thousands of dollars, you never have enough money. So if you can save money by using fewer subjects, that could be a benefit to you. You're able to look at changes over time because you have the same people in the two time periods, and so then you can really look at what happened during the. You can look at, you know, is there a big change over time, because these are the same individuals, so you don't have to worry about the variability due to, you know, differences in people. If you have the same person, any change is reflective of the intervention you're using, and not just random variability because you have different people. And that's what the third point means. It reduces the influence of individual differences. So when you have two samples of people, you have a lot of differences, and you have to weigh those differences versus the actual treatment and hope that the treatment is going to overpower any kind of individual differences. You don't have to worry about that if you're using repeated measure design, because individual differences is zero. You're using the same people. You don't have to worry about that. And that decreases variability. And if you decrease variability, you increase T. So repeated measures T is going to be more powerful, has higher statistical power, which means it's easier to reject the null hypothesis. That's a big advantage. But I said the downside is, you know, you have to really prove, you have to argue in favor of using repeated measures versus independent groups. You know, you want to make the point that we use repeated measures for this reason. You just don't want to do it arbitrarily. You want to have a reason for why you're doing it this way. Because there are some problems, and the problems occur when changes to the individual happen over time from external sources. So the disadvantage is stuff happens. For example, let's say you're doing this longitudinal or repeated measure design, and I'm measuring like what happens every year. So I'm measuring you once a year. Well, guess what? There's a lot of things that happen in a whole year, right? Things happen in the world. Things happen in your personal life, right? So these are what are called history effects and maturation effects. Things are happening in the real world, things are happening in your personal life, and they're going to influence your response, you know, at time two. Or it could just be that, you know, you show up at time one and then you don't show up at time two. That's a big problem. You know, I've run these kind of designs before in my research. And even if I do a 10-week study, I have people show up at the beginning and then they stop coming. They don't show up after 10 weeks. And so how am I supposed to do repeated measure design? You know, how am I supposed to do the t-test if they just don't show up at the end? That's the disadvantage, is because, you know, if you're doing independent groups, you're measuring them one time. You don't have to worry about them coming back. If you're doing the repeated measures, you have to worry about people coming back. Even if you pay them, they don't come back. If you tell them, if you come back, we're going to pay you, they still don't come back. because people, things happen in people's lives. They get busy. There's, too much school, too much work, too much family, and your study is not important to them anymore. And I don't blame them. I mean, obviously their personal life is more important than the study. But as a researcher, I just lost them. And now I have to throw out their data because they didn't come back. So that's a huge disadvantage of repeated measures, is if you spread out the repeated measure design, you may not have them come back. Even if you don't spread it out, you may not have them come back. It doesn't have to be a year period. It could be, 2 weeks. 2 weeks later, they may not show up. And that's called mortality. That doesn't mean they actually die. It just means that they don't show up anymore. So basically, you have to get rid of them. They can't count in your analysis. And this could be really frustrating. I've started some studies out with hundreds of people, and I've ended up with 30. And the reason I went from over 100 to 30 is because people stop coming. They don't show up. You call them, you email them, you beg them, you bribe them with money, and they still don't show up. So is it worth running the repeated measure design if you're so worried about your subject, not showing up? That's tricky. So there are a lot of advantages, but that's a huge disadvantage. There's also going to be order effects. For example, what if you gave somebody the drug first, and then you gave them the placebo second? Maybe if you give them the drug first, that's going to affect their response on the placebo afterwards. They're going to have some carryover effect from getting the drug first. So if the order in which you administer the treatments, in the case of a t-test, you have two conditions. If the order in which you administer them can influence the results, you have what's called order effects. And so then you need to counterbalance. So if you're giving, placebo and the drug to each individual, which I wouldn't advise doing it that way, but some people have run research studies that way. It's not advisable, but people do all kinds of things. You need to counterbalance if you're doing something like that, because the drug may affect what happens later with the placebo. So then half the people have to get the placebo first, drug second. The other half the people would have to get the drug first, placebo second. And that would balance out any possible order of the treatments. So that's called counterbalancing. That requires a little more effort on your part as a researcher, but if you only have two conditions, it's not a big deal. It's half and half. Half gets treatment 1 first, half gets treatment 2 first. And then you switch it off. The bigger problem here is not the order effects that require counterbalancing. The bigger problem is the withdrawal from the study, what's called mortality. That's a huge problem. If you're doing a matched subjects design or a matched samples design, you're not doing repeated measures. So repeated measures means you have the same individuals in both conditions of your study. With matched subjects or matched samples, you have actually two samples of people, but they're being matched on some relevant variable or variables. Like, let's say I wanted to match people on intelligence. I would find, two people with similar intelligence scores, and then I would randomly assign one person from that pair to group 1, and the other person goes to group 2. So I'd be matching them up on some relevant variable like intelligence or like socioeconomic status or whatever you think is relevant, and then you would randomly assign them to one of the two conditions. So you have different individuals in each group, but statistically you're treating them the same because they're being matched. So since you're matching them, you're treating them like the same person because they're matched on some relevant variable or maybe more than one variable, variables, multiple variables. Is that really effective? Is this the way to go? I don't like to do this kind of study. I guess you could do it if you had a reason for not running the repeated measures design, right? If you thought that there was going to be a problem with that, Could you match people up and then randomly assign them and then treat them the same? You could do that. I'd rather run a pure independent groups design, but there are situations where you can't randomly assign. Like for example, let's say you're studying people that have been abused. You can't assign someone to be abused and assign the other person to not be abused. Right? You can't randomly assign that variable, so it's hard to study that group with an independent groups design. But could I match people up in that study? Match people up that have been abused? Of course. That's easier than to actually randomly assign people to abused to versus not abused. That's not going to happen. So that could be a situation where you're going to use the match group design. But in a large majority of research, it's just, to me, it's too much trouble. It's too much work. I'd rather run either independent groups or repeated measures and not try to go in between here with match groups design. I'm not a big fan of this. Unless you have to, if you're studying something that you can't randomly assign, then I guess you could try to use this kind of design. Let's take a look at these last learning checks. Assuming that the sample mean difference remains the same, which of the following sets of data is most likely to produce a significant t statistic? So remember, to get a bigger t, we need a bigger sample size and we need smaller variability. So we want a large sample with small variability. Well, A has a medium sample, small variability. B has a medium sample, large variability. C has a large sample, small variability. D has a large sample, large variability. So I want large sample, small variability, so my answer has to be C. C gives me a larger sample and gives me the smallest variability, and that's going to give me the largest t value. Let's look at this true-false. Compared to independent measures design, repeated measures design reduces the variance by removing individual differences. That makes sense. There's less variance. If I'm using the same person in two conditions, there's less variability compared to using two different people. So that's one of the advantages of repeated measures design. And the repeated measures t statistic can be used with either a repeated measures design or match subject design. That's also true. I prefer repeated measures versus match subjects because match subjects, you still have individual differences, so you're going to have more variability there. Even though you're treating them as the same people, you're only matching them on a certain number of variables, or maybe even one variable. So it's hard to treat two different people the same if they're matched on only one variable. But you're using them, statistically you're treating them the same, but from a paradigm perspective, research design perspective, they're not the same people. So that just sort of underlies my real hesitancy to use the match subject design. But yes, we treat them statistically the same, so we use the same t-test. So these are true statements, both of these. So using the same subjects in both treatments removes individual differences. That's the advantage of using repeated measures t. And if I use related samples, that also reduces individual differences, but not the same as using the same people in both samples. So I'll have to say that again. Try not to use match groups design. It's just, or match samples design. It's not ideal, and I really never use that. So okay, so hopefully that walks you through some of the basics. Remember, treat the repeated measures t-test or the paired samples t-test the same way as you're doing the single sample t-test, except that you're using different scores instead of raw scores. It's the same calculation. Hopefully that helps a bit, and we're going to move on to ANOVA, which is going to be a little bit more complex, and then we'll get into correlation and chi-square to finish things off. But this will end the discussion of T, and we're going to move above and beyond to ANOVA, which is more than two groups for next week. So bye for now, If you have any questions, email me, come to office hours, etc. Let me know what's going on, and I'll try my best to accommodate you and get back to you as soon as I can. And just keep working at it. It's difficult, but just keep plowing ahead with it, and it's going to be all good in the end. But please contact me if you have significant concerns or questions as well. So bye for now. See you next time.